Let's now go to more advanced kind of ensemble models. So let's start with the bagging model. So in bagging model, what happens is that, like what we were doing just now, right? So you can use different training sets, okay, and you can build different decision trees. You different decision trees give you different forecasts, and you can average them. So this is the overall scheme, that you train same decision tree, okay, train same decision tree on different subset, and then you finally uh, add the forecasting. And for this type of model, though it is not necessary that you have to use only decision trees, you can use other kind of models as well, but it is a standard practice because of the qualities that I talked about. The decision tree is used as the base model. Okay, and one of the thing that happens is, when you take the samples, you take bootstrap samples. So what is this bootstrap samples? Bootstrap sample has two characteristics. The characteristics are like this. First characteristics is that the sample will have same number of observation as the original set of data. The second characteristic is that it is sampling with replacement, or it is sampling without replacement, or it is sampling with repetition. So same observation can be picked up. So here, if you see the first sample that we have produced, we have got 3, 1, 3. So 3 has been picked twice. Second one, 1, 2, and 3 has come individually, or separately. Again, here 2 has come 2 times. Okay, so this is a bootstrap sample. Why do we do that? We do that because that makes sure that my samples are varying quite a lot from each other. Okay, so that is the reason. Because as I make my samples vary quite well from each other, of course my trees will be more and more diverse. Okay, so here are some of the remarks. So one of the techniques, one of the things is that all the classifiers can be trained in parallel. So this is one of the advantages, because see, these samples are independent of each other. So the decision trees can be trained in parallel. Okay. Now, what we did sampling with replacement. Okay. And if it is without replacement, then it is called as pasting. Okay. So probably I gave you a confusing term. So just remember that when you are allowing this repetition, then it is bagging. When you do not allow this repetition, this is called as pasting. So it turns out that bagging, when you use bagging, you have similar bias, but you have a lower variance. Okay. So when you are comparing bias and pasting, it has similar bias, but has a lower variance. Okay. And bagging generates more uncorrelated trees than pasting. So actually, as it generates more uncorrelated trees, it has a similar bias, but lower variance. Okay. And this you have already understood, but nevertheless, let's go through this once more. So you have this training sample where you have different test samples being created, so which are actually training sample for these learning algorithms. And you have classifier 1, classifier 2, classifier 3, which are used in this combined classifier. Now a new data comes and you get the prediction. So this is used in the mathematical notation like this. Okay, particularly this will be useful when we are doing a regression. Okay, why this is 1 by m. So what this AIX denotes? AIX denote the prediction of the ith predictor. Okay, and you are taking it over a m predictors, and you are taking an average. Okay, so that's the idea. Okay, and gradually I will also make you familiar with some of the algorithm notation, because this is something you cannot do away with. Okay, so the industry is full of people. So this I have heard from my friends, my colleagues, who are in senior position as industry leaders, who recruits, as well as data science team leaders, that given a package, people can implement any model. But when you need to tune that model, when you need to improve the model, you need to understand the logic behind it. And a lot of the things, I will say that there is actually gold mine, okay, which is there in research papers, as well as gold mine which are lying there in these Kaggle notebooks, which are part of this competition. Okay, so and if you really have to come up with some or apply something which is state of the art, you need to develop a habit of reading them and trying to make sense of the different algorithmic notations. Okay, all right. So here is a quick comparison on effect on error. Okay, so here what has happened is we have drawn the error, we have drawn the variance, we have also drawn the bias and the variance. Okay, so in numerical terms, the error of a single decision tree, which is in this case 0.25, okay, is actually comes from bias, which is 0.003, and variance, which is 0.015. When you are now using an ensemble through bagging, okay, what is happening is you have a bias of 0.004. So the bias has gone up, but the variance has reduced. And what is this? What is this? So, the error which cannot be reduced, which is also often called as the Bayesian error, the lower bound of the error, okay, which is not reducible. Okay, this is what is common for both of them. Okay, so this is the entire error, this is the irreducible part, this is the reducible part, and you see that the total error has actually gone down in case of when you have just used a simple bagging based ensemble technique. Okay, and I have earlier also talked about decision boundary. So when you have such a kind of a scenario, these are the two classes, and you want to separate them out, decision boundary will end up, one single decision tree will end up having a decision boundary like this. But if you use a bagging based decision boundary, you will have something like this, which is much more smoother. Okay, all right. So this comes from a case study from a research paper where they tried to see that this credit scoring task. So when you are trying to decide that whether you are going to sanction a loan or not. Okay, so these people applied this on data sets like Australian credit data set, China data set, German credit data set. So let me not go through all of them. Let's just focus on Australian credit data set. Let me again not go into type 1 error and type 2 error. Let me just focus on these two columns. Okay, Australian credit data set, this much and this much. So here you see that there are 4 type of models which were being used. So this is logistic regression, okay, decision tree, artificial neural net, support vector machine. And see, it is reporting the mean and the standard deviation. So standard deviation you can roughly take as the variance, okay, roughly. So you see that the mean is 86.56. And when you have just used a bagging, it has increased this by 86.64. Okay, and this standard deviation also have gone little bit down. Look at the decision tree. There is an improvement by 2% over here, and there is a reduction in standard deviation. Look at ANN. There is again an improvement by 1 point some percent, and SVM there is a very little development. But this probably, so there are 2 things that you can again conclude from here. The conclusion is that as you use bagging, your accuracy more or less increases. Okay, you can get some samples probably where it is not increasing a lot or maybe at same level, but generally it is expected to do so, because if you have a particular very typical kind of data, it depends a lot on the data also, right? How your decision boundary is. Okay. So if you have a very typical kind of data, it may not work, but in general, you will see a improvement by certain percentage. Okay. And the variance, okay, will also go down. Also, there is another interesting observation that compared to all models, which model has highest improvement in terms of result? Okay, it is the decision tree. So that probably tells you that why decision tree we have studied, and decision tree is used in 99% of the cases when we are doing a bagging. Okay, but this also tells you that other machine learning models can also be used for bagging.